Okay, so I was talking about the optimum case. So let me write the statement. I will call it case 3. And the case number 3 deals with the situation uh, under which condition maximum power will be delivered to the load. So this question can be answered uh, using mathematical analysis on power. कि हमारे पास जो power की जो general expression है वो ये थी. General expression of power was that power is equal to 1 by 2 magnitude square of Vg into Rn divided by Rn plus Rg whole square plus Xn plus Xg whole square. ये हमारे पास वो general power की expression. Now, if you look at this equation, and I have pointed out it out before as well, कि ये जो power है ये डिपेंड कर रही है आर एन के ऊपर और एक्स एन के ऊपर. अज्यूमिंग कि हमारा जनरेटर और सोर्स जो है वो फिक्स जनरेटर है, तो वी जी भी फिक्स हो गया, आर जी भी फिक्स हो गया, एक्स जी भी फिक्स हो गया. सो अंडर फिक्स जनरेटर सिचुएशन कि जनरेटर को हमने चेंज नहीं करना, ट्रांसमीटर को चेंज नहीं करना, तो ये पावर हम कैसे इंप्रूव कर सकते हैं, ऑप्टिमाइज कर सकते हैं. इट डिपेंड्स ऑन दीज टू थिंग्स, दैट इज डिपेंड्स ऑन आर एन एंड इट डिपेंड्स ऑन एक्स एन. सो लेट मी राइट दिस स्टेटमेंट. Or meanwhile, I can share the attendance link of today's lecture. So in the chat window, now you can access the attendance link of today's lecture. So before I finish this lecture, you people can mark your attendance. So what I want to say about this case is, assuming generator is fixed, VG and RG, power, that is P, is dependent on Rn and Xn. So, in other words, I can say that power is a function of two parameters. It is a function of Rn and a function of X. So we can make use of a general mathematical rule that if you want to find out the maximum or minimum value of any function, which is a function of 1 or 2 or any other number of parameter, you take a derivative of that function with respect to that parameter, and then you equate it equal to 0. And from that particular uh, condition, you will end up with the value of that parameter for which the function attain its maximum or minimum value. Right now, we are interested in finding out the values of Rn and Xn for which this power becomes maximum. Okay, so what I will do is I will take the derivative of P with respect to Rn. I will take the derivative of power with respect to Xn and equate it equal to 0. And from that equality, I will be able to find out the condition for maximum power. Okay, so what you need to do is you need to take the derivative of power with respect to Rn and then equate equal to 0. And you also need to take the derivative of the power with respect to this variable and equate equal to 0. So I'm not going to do the step-by-step derivation procedure. We are more interested in the final condition. So this power expression आपके सामने है. इसका with respect to Rn आपने एक दफा derivative लेना है और एक दफा with respect to Xn लेना है. ठीक. So I'm going to write down कि आपके पास derivative लेने के बाद क्या result आएगा. ठीक है. So from this you will get Rg square Rn square plus Xn so you will end up with this, and from this second derivative you get Xn into Xn plus Xg equal to 0. Now, if you look at these two equations, we can easily identify the condition for which power will be maximum. If you look at this condition, this one, which is more easy, so first I will try to interpret the meaning of this equation. So this condition is telling us that xn into xn plus xg is equal to 0. So there are two possibilities. Either we will say this condition is true if xn is equal to 0. If xn is equal to 0, so the left hand side will become 0. Or other possibility is that xn plus xg is equal to 0. So both of these possibilities, both of these cases are mathematical possible interpretation of this one. But if you look at the first possibility that xn is equal to 0, so if you remember, we have already considered two cases, and out of these two cases, one case was that load is matched to the line. So this case is exactly similar. This xn, if you take this case that xn is equal to 0, so this is actually which case? Load is matched. Okay, so it means this case is not going to give us something different. This is the case which is going to make a difference, and that is this condition is telling us that x in equal to minus xg. And once you have this condition, you can then come back to the second equation that you have used, you have derived this one. So if you put x in is equal to minus xg over here, so this will be 0, and then you have r in equal to rg from this, because rg square minus rn square will be equal to 0, and then rn equal to r. So now you have a key condition, and that is telling you that if Rn is equal to Rg and Xn is equal to minus Xg, so what you can say about the relationship between Zn and Zg? क्या relationship होगी जी Zn और Zg?
सर कंजुगेट होगा ZG का
Yes,
कंजुगेट.
yes. You will say Zn must be equal to the conjugate of Zg. So ये जो third case हम पढ़ रहे हैं, इसको हम कहते हैं conjugate matching case. Conjugate matching. So now we have found the best possible condition. If you have a complete circuit where you have a source transmission line connected with a load, and you want to get maximum power out of the generator that is delivered to the load, you can make use of the condition that is known as conjugate matching. And according to conjugate matching, if you make sure that Zn is equal to Zg conjugate, you will get the maximum power. Now let's put this condition in the general expression of power so that we get the we can find out which expression is valid. So the original expression is this one. So you need to put Rn is equal to Rg. Okay, Rn is equal to Rg, and Xn is equal to minus Xg. So this term will cancel out. So this term will cancel out. You will only end up with, so let me write it over here. How much power will be there? It will be equal to 1 by 2 Vg magnitude square Rg divided by Rg square plus Xg square into 4. Sorry, मैंने mistake कर दी, sorry. Xg to cancel out. Let me go back. What is the condition? Rn is equal to Rg and Xn is equal to minus Xg. So sorry, मैंने इसको गलत कर दिया, cancel out हो जाएगा. So let me write the correct result. It will be simply 1 divided by 4 Rg. So whenever you say that the circuit is conjugate matched, in that case, you can make use of this expression for power. So this is power delivered to the load under conjugate matching. Now let's move on to lossy transmission lines. Till now, we were assuming that we live in an ideal world where there are no losses. And based on that, we analyze number of transmission line possible cases. But we know that in real world, there is no such thing as lossless transmission line. There will always be losses. So now we want to incorporate losses in our analysis. But we will limit ourselves to the cases where there are losses, but those losses are not that much. In other words, we will focus only on low loss transmission lines. And this makes sense because any manufacturer of transmission line, they will ensure that the transmission line that they are making, their losses are minimized, or they are having as less losses as possible. Because if someone design a very lossy transmission line, so maybe not many people will be interested in buying such transmission lines. Okay, so even though losses will be there in practical transmission lines, but those losses will be low loss. As a result, we will only talk about low loss transmission lines. Okay. So what I'm saying is, in practice, transmission lines have losses. And why they have losses? Because the conductor and dielectric that are used to design or manufactured transmission line, they all are having finite conductivity due to finite conductivity and lossy dielectric. However, these losses are usually small. In many practical cases, losses may be neglected. So because we are saying that losses are usually small, so as an approximation, you can assume that as if there are no losses. So that can simplify your uh, circuit analysis. Okay, but in many and sometimes you have to include, you have to quantify the losses to get a better idea about the circuit performance. So in many practical cases, losses may be neglected. But sometimes the effect of loss may be important, such as when dealing with attenuation, attenuation of a transmission line. For example, you want to find out how much attenuation is taking place in a transmission line. So then you have to find out the losses, because attenuation is because of the losses of transmission line. Sometimes you also need to find out the losses because the effect of noise of loss of transmission line, it manifests itself in terms of noise. So noise introduced by a lossy line. Or sometimes we need to find out something called quality factor, which is abbreviated as Q factor, of a resonator circuit. So it means that we cannot always ignore losses of transmission line. And these are some of the cases that I have pointed out. So whenever you are solving something related to attenuation, or something related to the noise, or something related to the quality factor of resonator, then you have to quantify the losses. So as I have already pointed out, our focus will be on such lines which have small loss. So such type of transmission lines are known as low loss line. Low loss line. So before we derive an expression for propagation constant of low loss line, let's quantify, because just by saying low loss, it's not complete information, because what is the benchmark for low? So I may have a different, totally different interpretation of this word low as compared to any other person in the world. So we need to be sure that everyone is using the same benchmark so that we can say that this transmission line is low loss or it is of heavy loss. Okay, so the criteria that we use for saying that this transmission line is low loss is based on this, that the resistance of the transmission line is very, very small as compared to the omega L, the inductive reactance, and the conductance of the transmission line is small than as compared to the capacitive reactance represented by omega C. So if transmission line, if it fulfill this condition, then we will say that it is a low loss transmission line. Okay, so this is the condition that we are going to make use of. Now, for general expression for propagation constant is, so general expression for propagation constant that we have derived before is equal to R plus j omega L into G plus j omega C under the root. So when we were deriving or talking about the transmission line theory, in which we represented the transmission line in terms of its lumped element model, so during that particular discussion, we derive the expression for of propagation constant of a transmission line. Okay, so this gamma is complex propagation constant, and it depends on these three factors. I want to make use of this condition. Okay, I want to see what is the effect of this condition on this propagation constant. So for that, I want to rearrange this expression. So what I will do is I will take j omega L as constant from the first term. So I will end up with 1 plus R divided by j omega L. And in the second factor, I'm going to take j omega C as common. So I get 1 plus G divided by j omega C. So this is what I can do. And then you can take these two factors outside, this one and this one. So you get propagation constant is equal to j omega LC under the root. And we are left with 1 plus R j omega L into 1 plus G divided by j omega C whole under root. So this is what you get. And then you can multiply these two terms, these two complex terms together. So you will get j omega LC under the root. And you get 1 minus j R divided by omega L plus G divided by omega C minus RG omega square LC under the root. Now at this stage, I'm going to make use of the condition, and that is, if you go back, low loss line R is very, very less than omega L, G is very less than omega C. So if now you multiply RG, it will be even more smaller than omega square LC. Okay, so their product will be even more smaller than this thing. So now if you look at this term is in the denominator. Rg divided by omega square LC. So it means this term is going to be so small for a low loss line that we can almost neglect it. So this is what I'm going to do. I'm going to say for low loss transmission line, we can neglect Rg divided by omega square LC. So as a result, we get an approximation. So now I will say propagation constant is approximately equal to j omega LC under the root and 1 minus j r divided by omega L plus g divided by omega c whole under the root. So I just neglected this term, okay? But again, I can only neglect this term if you are dealing with a low loss line. So that's the reason from equality, we now have approximately equal to. Now what I can do is I can simplify this result So I can represent the square root by 1 by 2, this to the power 1 by 2. And then I can make use of a series, that is a Taylor series. So using Taylor series, we can expand the bow expression So you can make use of Taylor series and apply that Taylor series on this thing. However, we are not going to, Taylor series is infinite series, so I'm not going to use all of the terms. We know that the initial terms are more significant. So we use the first two higher order terms only. So you people already know about Taylor series, so I'm not going to talk about that. So you can look it into any basic engineering book, engineering mathematics book. So you will get this thing, 1 minus j by 2 r omega L plus g omega c. So when you expand this expression, this one, but you consider only first two terms. So the first two terms are this one. This is the first term and this is the second term. Okay. If you still have some confusion, let me say that if you have something like 1 plus x raised to the power n, if you expand this expression using Taylor series, you get 1 plus nx, and then you get n into n minus 1, 2 factorial x square, and so on. So I am just taking these two terms. In our case, this is n. Okay, this is n, and this whole thing is x. Okay, so you can easily find out how I get this thing. Now let me simplify this and then ends today's lecture. So we get this thing. So gamma is equal to, let me multiply this term. So this term multiplied with 1, you get j omega LC under the root, and then multiply this thing. So minus and then j square. So this is also minus, you get plus, and then omega LC under the root divided by 2, and you have R omega L plus G omega C. Now you can clearly see that we have been able to separate the real and imaginary part. So this is J something, J something. So this is actually beta, the imaginary part of propagation constant. And if you remember, this is the same value as you get for the lossless line. So the phase constant or the imaginary part of propagation constant of a low loss line is the same as that of a low loss line. And this term, you can clearly see that is a real term. So this must be alpha. So what is alpha? Alpha is equal to omega LC under the root divided by 2 R divided by omega L plus G divided by omega C. So we know that for a lossless line, attenuation constant, that is alpha, was 0. But now you can clearly see that for a low loss line, attenuation constant is not 0, but it is equal to this thing. So phase constant is the same for both lossless or low loss line. They both have the same beta value. Okay, but for a lossless line, alpha is 0, but for low loss line, it is not equal to 0. Let me uh, also write this thing in a different manner. So let me multiply this so that we get the final answer. So this term can be first multiplied by this and then multiplied by this. So you can see that some of the terms will cancel out, especially this omega term. Okay, so let me simplify this, that alpha is going to be approximately equal to 1 by 2 R C by L under the root plus G L by C under the root. Okay, so when you multiply these two terms, 1 by 2 is a constant factor, so I have taken it outside. Okay, and then you have R, and because you have L under root and L, so this L under root will come in the denominator, and C under root will be in the numerator. C under root divided by N, and similarly you get this. So this is the attenuation constant, and you should remember the units of attenuation constants are Nepper per meter, and बीटा वैल्यू भी हमने फाइंड कर ली है जो कि ओमेगा एल सी अंडर रूट के बराबर है, which is measured in the units of radians per meter. So now whenever you are dealing with low loss transmission lines, you can make use of this expression to find out the attenuation of the transmission line, and you can make use of this expression to find out the phase constant of the transmission. Okay, also just a last point, the characteristic impedance, if you remember general expression जो हमने derive की थी कि किसी भी lossy transmission line का propagation constant इसके बराबर. Now because R is very much less than omega L, G is very much less than omega C, so R is less than omega L, इसका मतलब है कि we can ignore R. G is very much less than, so we can assume that G is 0, so J cancel out. So Z naught for a low loss line is approximated to be equal to L by C, and you can see L by C is a real number. So that is the reason whenever we talk about transmission line, we say a characteristic impedance of transmission line is 50 ohm. So you can see this is a real number. So all practical transmission lines, whenever you use them, whenever you use practical transmission line, जब आप उसकी characteristic impedance की बात कर रहे होते हैं, आप कह रहे होते हैं कि इसकी 50 ohm है, उसकी characteristic 100 ohm है, 75 ohm है. So you can see actually अगर Z naught को देखें वो एक complex number है, लेकिन क्योंकि real world में जो हम transmission line use कर रहे होते हैं वो low loss होती हैं, तो लो लॉस में अप्रोक्सीमेटली कैरेक्टरिस्टिक इम्पिडेंस की जो नेचर है वो क्या होती है, रियल होती है. ओके, दैट्स enough for today. Now before I end this meeting, if you have any question, so you can ask any question from today's lecture.
No, sir.
Okay, thank you very much. See you next time. Allah Hafiz.
Allah Hafiz, sir.
Okay.